My name is C. Nadaraj. I'm from Villanova University. Buongiorno. I'm very happy to introduce Professor Mahmoud Hussein, who actually met in Enoch. We spent a lot of time together chatting about his interesting research. He's the Alva and Hamiet Howlett Professor at Department of Aerospace Engineering, University of Colorado Boulder. After getting his PhD from University of Michigan, he had a stint as a postdoctoral fellow at Cambridge. His research focuses on dynamics of materials and structures, in particular phononic materials and metamaterials at both continuum and at atomistic scales. He has tons of publications, including an edited book on lattice materials, which is sort of an upcoming thing. He'll talk about flow control, very important problem of flow control using phonon motion in subsurfaces, about which I know nothing, and I'm looking forward to his talk to learn.
Thank you very much for the kind introduction, and also thank you to Professor Labarcanara for the invitation. This is the first time I come here and attend this conference, so it's a tremendous honor to be here. What I would like to do is to introduce you to a concept that we brought forward a few years ago that we call a phononic subsurface, or PSub in short. And I hope you'll find it interesting, maybe a bit intriguing. What it does is essentially it allows us to realize complete phased wave propagation in complete synchrony between an elastic structure and an interphasing flowing fluid. So not just a fluid, but a flowing fluid. So the elastic structure will be this, what we call the phononic subsurface, and I'll explain what it is shortly. And then the flowing fluid will be essentially a full-fledged 3D Navier-Stokes nonlinear flow, but one that is in a transitional state. So it will admit or carry with it a perturbation field. So that will be a flow wave that is traveling along with the mean flow. And what I'll present to you today is this unique ability to control that instability using this concept. So its importance, I think, stems from the fact that it allows us, in principle, to address quite fundamental problems in fluid dynamics, including transition to turbulence and flow separation and so on. So if we were to overcome the practical issues, potentially this could advance a new paradigm in aircraft design and fluid structure interaction in general. All right, so I'll start with a textbook picture. Everybody's familiar, of course, with this picture that demonstrates transition. So we know that in a laminar flow, essentially, we can possibly, in some instances, have an instability that may, or a disturbance that may come across due to different reasons. And that instability is, in fact, a wave, a linear wave that has a phase and that has a frequency and that has a wave number. And among several paths to transition is the growth of this instability. So what happens is that we can actually analyze that instability by solving the linearized form of the Navier-Stokes equation, and we can obtain its modal characteristics, so its frequency versus Reynolds number, so we can identify specifically which modes are unstable. So this is a picture from my late colleagues, Sadat Berenjen's simulation that gives you a visual sort of appreciation of what I'm talking about here. So you can see this is a transitioning flow, and you can see elements of the wave and then the gradual breakup. Now, what is really important, and all fluid dynamicists in the audience will know, that in a laminar flow, the skin friction drag is very low, whereas in a turbulent flow, the skin friction drag is very high. So it's tremendously beneficial to delay transition, because then you can significantly reduce skin friction drag overall on a wall-bounded flow. So if we go back to this picture, essentially this is just a way of saying that we want to push that line, that green line, further so that we gain that benefit of reducing overall drag. Now, the idea is that we would like to intervene in a rather sophisticated way, I believe, to stabilize that wave. And we would like to do it passively. So if we're able to do this, then the benefits can be quite large. I think it cannot be overstated. Just to give you an idea here, the $210 billion is an estimation of the fuel expenditures in globally, and the number of passengers are increasing rapidly. If you look at sea vehicles, because this also can be applied to marine vehicles, you can see the statistic here on the climate side. And then there's other applications that, very similar, land vehicles, wind turbines, long-range pipelines, and so on. Now, if we're able to intervene with this unstable wave to attenuate it, then in principle, we can also do the same to do the opposite effect, to let it grow at a faster rate. So that will be a destabilization rather than stabilization. And that, in fact, has its own benefits as well, if you're interested in delaying separation, or if you're interested in increasing fluid mixing, and so on. Okay, so I'll now look at the same problem. I've shown you a schematic that shows a boundary layer. I'm not going to go into now, just for simplicity, focus on a channel flow. So this is a very familiar parabolic profile of the base flow in a channel. And of course, this is assume we're getting this by solving the Navier-Stokes equation. It's nonlinear. The instability that I'm talking about will be a feature that adds to that small perturbation, that's why it's linear, that adds to that profile. And together, they will form the transitioning flow. Now, what happens is that as the flow progresses and the instability progresses, that instability grows. And this is really where you begin to see the very early birth of turbulence, in the sense that the profile momentum transfer takes place outwards, and you begin, and this is an exaggerated view, of course, but you begin to see this qualitative change in the profile, and it's all because of that instability. All right, so underlying this mechanism is a delicate energy transfer. Obviously, the instability needs to get its energies from somewhere, so it gets its energy from the mean flow, and then gradually, that's how it grows and becomes dangerous, in the sense that it would lead to breakup. So this was just a quick intro on that side, on the fluid side. Let me now take an aside and share with you some really basic structural dynamics ideas, only for context, so that you can see the full picture. So if we have a structure, so now I'm transitioning to a structure. If we have a structure and we excite it from the top harmonically, and we measure the input velocity, so the velocity where we excite the structure, so that's why I'm calling it input velocity. Suppose we excite at a resonance, then we track the input velocity, so the velocity will be as shown there in red, and you can see if you zoom in. Now, on the other hand, if you excite that same structure at an anti-resonance instead, with the same forcing amplitude, you will see that the amount of energy that comes in is less. So even though the forcing amplitude is the same. So this is, in fact, the essence of resonance and anti-resonance, as we all know. You need to put more work on the same structure with the same forcing if you're in a condition of anti-resonance versus resonance to get the same energy into the structure. And you can see that clearly in this contrast. All right, so this is resonance and anti-resonance concepts in a structure. What I'll show you now, and hopefully convince you, is that we can contiguously extend these basic ideas into the flowing flow, right? So, so going back again to this picture, in fact, one can view this energy transfer from the mean flow to the instability as a resonance phenomena. So energy is being added to the instability. And if we're able to interfere in a wave synchronized way with that instability, we can reverse the trend and reduce the amount of energy going from the mean flow to the perturbation, relatively speaking, reverse the direction, and that would be corresponding to an anti-resonance phenomena in the flow itself. So, so this is the basic premise. So now how will we achieve this? And we'll achieve this borrowing ideas from condensed matter physics. So condensed matter physics, of course, is a classical field where we look at waves in crystals. And this is, you can think of this as an enlarged crystal. This is a composite material consisting of a layering of plastic and aluminum. And it's designed with ideas from condensed matter physics. So I have another cartoon just to help you visualize the concept. So this is the instability. It's traveling. It's constantly exciting the surface. So if you're the surface of a wing, for example, you're constantly feeling vibrations from the top. The rigid wall part, which is this brown part, doesn't care, obviously, but the elastic part will feel the vibrations. So what will happen is that these vibrations will transmit into that structure, which we call the phononic subsurface. And then if we're able to design it in such a way that it will respond specifically at an antiphase, what it will do is it will cancel the original wave that is coming from the flow, and it will do so in the steady state. So, and then in principle, we're able to achieve our goal. So how do we do this? In fact, it's quite simple in terms of how we do this. So we start by looking at a single unit cell in this periodic structure. So we call this a phononic crystal. And you can plot the dispersion curve. So this is a wave number versus frequency, and you can see, so the x-axis here is the frequency. You can see a band gap, a range of frequencies where waves cannot propagate, and the black lines represent propagating modes. And I should say that everything is linear here. Now, on the other hand, if we truncate that structure and turn it into a finite structure, it's no longer a material, it's no longer an infinite media, it emits vibrations rather than waves. If we excite that structure, that same structure, we get a frequency response, as you can see here. In the amplitude is in the second plot, and then the phase in the third plot. If we were to multiply the amplitude by the phase, we get what we can call a performance metric, which is shown there in the bottom plot. So now suppose your instability in the flow is at a frequency that is shown there in green. So, and in that case, we would be interested in stabilizing that frequency, that perturbation. And indeed, if we would apply this phononic subsurface, it will stabilize it because that frequency intersects with that performance metric at a negative value. So negative value means negative phase. So, so that will essentially allow this cartoon that I showed you. What will happen is that the flow wave will turn into elastic wave, and it will reflect back at out of phase, so it will cancel the continuously incoming waves. On the other hand, if we were in a different scenario, if we're interested in destabilizing the flow, then we would design it such that it would hit the frequency of the instability would intersect with a positive value. So that would be the opposite effect. So that would be in-phase interferences rather than out of phase. Okay, so we can call this a theory. We call it a theory of phononic subsurfaces in the sense that it allows us to predict exactly what will happen to the flow and exactly in terms of the evolution of the instability field without even running a flow simulation. So we can predict everything just by doing these offline calculations, structural dynamics calculations. So this is it, in fact, and what I'll show you now is just simply a proof of the idea. So the rest of the talk will be testing it. So we will run fluid structure simulations. So this is, we will decompose in our analysis the flow field, as I mentioned earlier, into a mean part and a perturbation part. So this will be the base flow, and then we have the instability or the perturbation part, and then we'll add a random signal just for realism. So what we're interested in is in the instability, but now we're no longer going to excite the structure by itself. Rather, the excitation will come naturally from the flow. All right. So to test this, we need to do a series of 3 steps. First, we need to solve the Orr-Sommerfeld problem. So that's the linearized form of the Navier-Stokes equation, just to get the modes, pick up a mode of interest, and then apply it, and that will be the second step, apply it to a full-fledged coupled flow structure simulation, solve the Navier-Stokes. And then the third step would be to track the instability. So the first step, and I'll be quite quick, this is just an eigenvalue analysis. For a given Reynolds number, you can get a frequency of interest. So that'll be the instability we're interested in. We'll pick it, we'll apply it. Then we'll run the simulation. So these are the Navier-Stokes equation in the main channel. The solid itself, will solve it using finite elements, just a standard elastic medium. And then we'll apply flow structure boundary conditions. We apply what's known as the transpiration boundary conditions. Other boundary conditions can be applied as well. Okay, so we can then, once we run the flow, we have to run it for a long time to ensure steady state. We can then monitor or measure the kinetic energy associated with the instability itself to see what happens to it. So if the kinetic energy decreases, then that implies that we were able to stabilize the flow, and vice versa if it increases. All right, so here's the results. The first set of results I want to show you. So what is shown on the left is done offline, done a priori. So this is the performance metric that I showed you before. The green part represents the region where if the instability hits that green part, we'll get stabilization. The red part would be the one that will give us destabilization. On the right is actual results. So this is the kinetic energy of the instability initially before applying the PSub. So this is just having a rigid wall. And you can see as we move downstream, the kinetic energy of instability increases, which is expected, of course, because it's an instability. Its kinetic energy is increasing. Now, we will consider that first case where we have an instability that corresponds to that frequency here, and then repeat the experiment in the computer, and you will see that the energy of the instability drops exactly between the two vertical lines. These vertical lines represent what the PSub is. So, and then afterwards it's recovered. So essentially, it has done what we wanted it to do. On the other hand, if we apply in another experiment, a case where the frequency is shown there on the darker line, where the performance metric is still negative but stronger, we will again get stabilization but stronger, as suggested by the performance metric. In contrast, if we apply a frequency there on the left, that same PSub will destabilize by design rather than stabilize because it intersects with the red part, and indeed you'll find the kinetic energy of instability growing where the PSub is rather than decaying. And then if we apply a stronger one, also as expected, it'll grow rather than drop. So we can then essentially view this as a design approach. We can design different PSubs, just like Lego sets, that gives us stabilization and destabilization as we desire. Imagine putting this in the subsurface of an aircraft wing, for example. Now, let me show you the first of two simulations. This one is essentially exactly what I was showing. It's a case for stabilization. This is the same simulation. The one on the left has the camera fixed, whereas on the one on the right, the camera is traveling with the instability. Have a look at the third slot. This is where we'll apply the PSub. The PSub will be applied at the middle of the simulation. The color profile here represents the intensity of the one component, the U component of the instability. So red means high intensity, yellow means low. So you can see the instability is traveling. So this is the flow traveling. And then the PSub will be applied. And it's quite subtle, but if you look carefully at the third slot, you'll see that it turns more yellow, which implies that the instability has been stabilized exactly at that slot. And you can see it more profoundly here in this still picture compared to the reference case where there's no PSub applied. So this is another simulation now showing the response in both the PSub and the full instability field in the flow. And you can see there on the left, the energy in the PSub is very minimal, and that's because it's a negative phase effect. It's an anti-resonance effect, if you remember the structural dynamics textbook problem that I showed you. And correspondingly, in the flow itself, it's minimal. Whereas in contrast, in the other case, it's high because that's an in-phase effect. which again corresponds to what I showed you before, that if you excite at a resonance, the structure will resonate. But what is interesting here, that this resonance will transmit through and impact the flow equally, as well as just like it would with the structure. So you can see it even more here. So this is the energy of the PSub and the energy of the instability in a case where we want to stabilize. And you can see exactly where the PSub is included, the color contour drops. To put this in contrast, this is the rigid wall case, so nothing is happening. And in fact, if we design a PSub that just designed to be neutral, you'll see that it's exactly like the rigid wall case. Nothing is happening, which is reassuring. On the other hand, if you apply a destabilization case, you'll see that the energy exactly where the PSub is increases. So this is quite remarkable, I think, because it shows perfect synchrony between phased wave phenomena, between an elastic structure and the flowing fluid. So we heard the quartet this morning playing music for us, and it was music to our ears, but I think maybe we can consider this also music, maybe not to our ears, but to the mind of a wave propagation dynamicist who can appreciate this notion of complete synchrony between waves in an elastic structure and a flowing fluid. So what I've shown you before is a long phononic structure. Because it's a phononic crystal, it's 2 meters. It's not practical, obviously, but we can utilize other ideas from this field that we call phononics and employ a metamaterial. And I won't get into the details there, but we take it to much smaller sizes. And again, if we contrast, this time it's even more profound. You can see the two opposing effects between negative phase and positive phase. So, and we can even calculate the skin friction itself, and we see a correlation between the energy increase and decrease in the instability and the skin friction. So we basically realized this intervention into the energetics between the mean flow, which is a nonlinear flow, and it's the instability, a linear instability carried by that mean flow. We can even dig deeper into this and look at the production rate, rigorously look at the production rate. So without any PSub, you see the production rate increases just a little bit further from the wall for an instability. Whereas once we apply the PSub, it reverses. So there is negative production rather than positive production. And then at the downstream of the PSub, it reverses back again, which is consistent with what I showed you before. And the whole thing reverses for the destabilization case. We can then extend this to multiple PSubs. Suppose we want to cover the full extent of a wing, for example, and you can see it's self-explanatory. You can see that we can extend the effect across multiple PSubs, and we can also extend the friction drag across multiple PSubs. So finally, I'd like to share with you that essentially with this approach, we can come up with a figure of merit, which is this area under the curve there in green. What we would want in future research is to extend, broaden that area to cover a broad frequency range, to cover multiple instabilities, which would be more realistic, and then also deepen it to make it stronger. So that would be a figure of merit for stabilization, and similarly, the area under the red curve would be a figure of merit for destabilization. I like to make a contrast with solar cells. When solar cells emerged in the 60s, the efficiencies were very low, but it was a new concept, and different groups in the world advanced it with time until now solar cells have proliferated. Hopefully we can see something similar with PSubs, where different types of research, especially in the phononics field, which includes a lot of nonlinear ideas, can advance these performance metrics until we reach a point where we can have it valuable enough for industrial proliferation. So finally, one can then envision, maybe dream a bit, how an aircraft in the future can look like with this technology, whereby we have subsurfaces introduced, specifically designed to interact with the flow and gives us a more fuel-efficient flight. So finally, I'd like to make some acknowledgements in addition to the sponsoring agencies that I showed there on the right. It's been really a long journey going through this research. Of course, I have to start with my students, especially Armin Kianfar, who's done a lot of the research, especially the new research results that I've shown you today. Collaborators, I'm listing here a few of them, including my dear friend Sadat Berenjen, who's a fluid dynamicist. He and I started this together earlier on when I joined the University of Colorado Boulder. And this is a special moment, as I say here, because this is the moment the whole team, early in 2014, after several years of exploring this problem, finally found the recipe, which I shared with you today, a very specific recipe that allows us to synchronize a wave in an elastic structure along with waves in a nonlinear flowing flow. So with that, I'd like to just bring just summarize the concluding remarks here. We've shown you wave motion being phase synchronized for the first time, I believe, between a flowing flow and an attached solid. This allows us to control with command passively complex fluid dynamics phenomena by subsurface phonons. It brings together several fields, fluid dynamics and condensed matter physics and so on. And here are a few references if you're interested to learn more. So thank you very much.
Hello. Thank you very much, Mahmoud. Very interesting talk.
Thank you very much for the talk, and it's impressive. I have a question. You stabilize it locally, and then it seems the perturbation kinetic energy increases even much more than than the neutral case, which means that transition now is going to happen faster. So, are you really controlling the stability?
So this is a very good question. So in fact, we realized that there's a trade-off between the strength of the reduction and the recovery. So if you would like to get good recovery, you will sacrifice the strength a bit. That's the first point. But secondly, what I've showed you at the end is the possibility of applying several PSubs adjacent to each other. So you would, in principle, cover the whole region of interest. So effectively, you will delay transition in that manner. I should also add that we have new work that is just appearing right now that employs further ideas building on this concept that causes the effect that we're interested in downstream. So that's coming.
One. In the 90s, there were experiments with the skin of dolphins, and there was a big discussion whether they are passive or active interventions. So do you have any comment on that with your view?
Indeed. So the skin of dolphins was a phenomena that was observed. It was intriguing, but there was no underlying theory. So what we have now is a concept where there's a very rigorous underlying theory involving wave mechanics. So we can now repeatedly obtain the result we're interested in, and we can predict it before we even run a simulation. That was not the case when in these compliant coating studies that mimicked dolphin surfaces.
So do you have plans to do cut up dolphins and put phononic surfaces?
That's not part of the plan.
Okay, just confirm me. Last question.
Yeah, thank you very much for the interesting talk. My question is whether you necessarily need a plastic structure, a periodic structure, because I can imagine that you need just a structure that allows the existence of evanescent waves, and it can very well be a non-periodic structure. Am I right?
Absolutely, you're right. However, it won't be as effective. So this is the beauty of the field of phononics. I actually come from that community. I invite you to explore that community. I think Walter is also part of that field. Phononic materials and structures allow you to tailor the response in a manner that you can't achieve with a normal homogeneous structure. So you can get a broad frequency range that is impossible to achieve, and you can get low frequencies that is impossible to achieve with standard structures. But I wasn't able to get into that level of details there.
Thank you very much, Mahmoud.
Yeah.
We have to draw the close now. So
Thank you so much.
thank you for attending the morning.